So welcome everybody to the IEA Bioenergy Webinar series hosted by the Canadian Institute of Forestry. And my name is Ronnie Huang, and I will be moderating today's session. Now today is October 27th, 2016, and we are very pleased to have all of our presenters and speakers today. And I will pass it on to Jaap to introduce our speakers.
Yes, hello, Ronnie. Thank you for that. I hope you can hear me.
Yep, we can all hear you.
Okay, good. We have some problems with the phone on this side, but thank you for that introduction. And again, I would also like to welcome you, all of the participants in this webinar. It's a great opportunity, I think, for us to tell a little bit of the work that we have done as Task 32 and 40 of IEA Bioenergy. For those who do not know the work of IEA Bioenergy, this is a whole group of people working in different tasks on various aspects of bioenergy. And so I would like to invite you all to have a look at the website of IEA Bioenergy, ieabioenergy.com, in case you would like to know more about the various activities there. For today, we would like to share with you some of the work that has been done on biomass torrefaction recently. And that will be done by a few people that were active in two projects that we initiated. One of them is a report that was published by Task 32, which is the left-hand report on the status of torrefaction technologies at the moment. The other report is what was recently produced by Task 40, which is on biomass trading, and that shows the possible implications on international biomass trade. So both reports are available on the IEA Bioenergy website. So I would like to invite you also to download those reports to have a more detailed look. Now I think we'll go into the details of both reports. After the whole webinar, there's a Q&A session so that you can where you can launch your questions. And we will hopefully have some good discussion on this. Let's see if I can go to the next slide. Yes, for today, well, there are four people involved in the presentations. First, it's myself. My name is Jaap Koppijan. I'm in my daily life also managing director of a contract research company involved in bioenergy. So we develop bioenergy technologies there. I'm also a task leader of IEA Bioenergy. The second person who will present today is Marcel Kremers. He is a senior consultant at DNVGL in the area of thermal power generation and has been involved in many technological reviews and feasibility studies, tendering procedures, etc. He has also been involved in Task 32 for a long time, and he is one of the lead authors of this report that we present today. He is also, well, involved in many other activities in Task 32. The third presenter today is Michael Wild of the International Biomass Torrefaction Council. He has been active in renewable energy for a long time, over 25 years. First in biomass-fired district heating systems in Austria, but also conversion of coal-fired boilers to biomass, for example. He has been involved in biomass trading for over 15 years and setting up also supply chains from Asia and North America to Europe and to Japan, for example. He has also been involved in torrefaction technology for over 10 years. First with Andritz and now, as I said, also president of the International Biomass Torrefaction Council. Michael is also active in Task 40. So with these people, then we also have, of course, Martin Junger. I should not forget him. He's the professor of bio-based economy and the leader of Task 40, which is on international bioenergy trade. He's a full professor of bio-based economy at Utrecht University, where he leads a group of about 5 senior and 15 junior staff people working on bio-based economy issues, including torrefaction. So with this, I would like to go to the contents of today, just by introducing the topic of torrefaction. What is torrefaction about? Well, basically, it's simply said, it is something similar than as roasting coffee beans. We heat biomass to a temperature of about 250 or 300 degrees centigrade in the absence of oxygen. And by doing that, of course, the biomass dries, but it also roasts a little bit. Part of the volatiles are removed, and that gives different characteristics to the biomass. So this is very simply said the process. And as you see in the picture on the right-hand side, you can roast coffee beans in different degrees by changing the process conditions. And this is also what you can do with biomass. You can, depending on the temperature of torrefaction, you get darker or lighter biomass. Moving on to the next slide. What are some claims made by companies involved in this torrefaction process who have tried to develop this process? Well, claims made on the first place that by doing this you can reduce the amount of volume that is contained in the biomass. So the volumetric energy density increases, and that could lead to cost reductions in logistics. Then by reducing logistical costs, it could be possible to transport biomass over longer distances and increasing the feedstock base geographically, or maybe even use a wider variety of feedstock. Then by roasting biomass, torrefying biomass, the biodegradation is reduced, so the biomass becomes more stable. You can use it in a larger variety of applications, not only biomass co-firing, but also some other processes, which Michael will talk about later. Then in the back end, if you talk about a coal-fired power station, you have a fuel that is more compatible with coal, so it might reduce capex and opex costs on that end side in terms of grindability, for example, and water resistance. Then the combustion and gasification behavior becomes more compatible to coal. So basically, if you sum up all these issues, we are producing a fuel by torrefying biomass that is more compatible with coal. So easier to feed into existing infrastructure. And by doing that, we can help the market towards more commoditization, making a standard fuel, and increasing the volumes of biomass that are traded internationally. So how does this work? Looking at the energy balance, if you look at the amount of biomass that is converted into torrefied biomass, we see here just an example of an energy balance, mass and energy balance, where black shows the heating value and red is the amount of energy, and blue is the amount of mass. In the end, you see that by drying biomass, you lose, of course, some of the moisture and some of the volatiles, so the amount of mass reduces significantly. Then further torrefying it, the amount of mass is about 1/3 or so of what we started with, while the amount of energy that is that we have in the final product is almost the same, just slightly less than what we started with. So the heating value increases, and the amount of mass reduces significantly. So if you after torrefying have a densification process, and also the volume of the biomass reduces significantly, and we can have these polymetric a graph that is in the first report that I mentioned that shows a little bit of the basic principles. If you start with a dryer with an efficiency of 90% and or 80%, I think we assumed here, and you see here some typical conditions where torrefaction could operate. Say in this case 45% moisture content. The different lines here show different lines of dry mass loss. So if you reduce 30% of the dry mass during torrefaction and start with 45%, then you could have an energy efficiency of over 90%. So this is typically what most processes operate at the moment. So this proves that, or more or less illustrates that torrefaction can be energy efficient. So some technical challenges remaining where various developers have struggled with is the water resistance of the product, pelletization of torrefied biomass, which is sometimes difficult to achieve. I think we have made quite some progress recently in this area, but still this was one of the points of attention. Several process owners were unable to meet constant quality requirements and struggled with their process control, for example. Another issue was that the dust formation of torrefied wood pellets that could be significant and also create a health and safety issue. Then finally, the ash content, of course, increases if you torrefy biomass, because the amount of mass reduces significantly, but the ash still remains in the product. So, on the other hand, we see that the chloride could, in some cases, be removed during torrefaction, which is quite an advantage for combustion processes. This is just one of the slides in the report that shows the impact of changing from coal to torrefied wood in a pulverized coal boiler. Some CFD calculations where you see basically the shape of the flame, which becomes larger if you switch to torrefied wood pellets on the right-hand side. And the reason for this is the fact that we have more volatiles in the torrefied wood. So basically, there are some issues also during conversion of the fuel, but looking at the impacts, our conclusion is that these are all manageable. With this, I would like to conclude my introduction and switch over to Marcel. Marcel, welcome back.
Okay, yeah, thank you very much. Thank you all for listening. Well, this is, let's say, the section I will be presenting is about commercialization of the torrefaction technology. And it is mostly based on the work what we did in 2014 and early 2015 on the status of biomass torrefaction within task 32, and which can also be found in the report. The first thing we looked at is we wanted to have an overview about what is the current status of the torrefaction technology as such. And therefore we did an inventory along all different or many different torrefaction developers about what is the current status, what is the capacity, and so on. So we performed an extensive round of interviews with many developers in the market. And from the consultations, we derived that over the years, the total installed capacity has increased to, let's say, somewhere around 150 kilotons per year. This includes all kinds of different demonstration scale facilities. And the demonstration scale facilities typically have a size of about 3 to 5 tons per hour of product output, which can be in the form of dust, or pellets, or briquettes. And this accounts for, if you would calculate that, how much that would be on a yearly basis, that would be about 25 to 40,000 tons per year. Most of these facilities have been built in the period of 2010 to 2014. And the current situation is that few of these plants are currently operational, and the main reason for that is the market conditions. As Jaap already said, we know quite well how the product looks like. Also, we know quite well where the deviations are with regard to product quality and how that can be managed. So the process is understood quite well, but the market uptake still lacks. So that was also a question about to the developers. So how do you think that the progress has been over the last few years? So that was a question we posed in 2014. and we said give it on a scale from 1 to 10, please rate, and then the average we got is 5.7. So just for completeness, this is an overview of different torrefaction initiatives that were present in 2015. It is not completely accurate anymore, but essentially I think the overview is still valid. What can be learned from this is that if you look at the scales, there is a variety of scales available. So there's from lab scale and pilot scale to demonstration scale. The largest facilities are somewhere between, let's say, 30 and 80,000 tons. Locations is mainly in Europe and the United States and Canada. And if you look at the status, is that from these demonstration scale facilities, many of the facilities are currently idle, and some of those could be made available when needed. So we also looked at research, just a global overview about what's the tendency in the topic of torrefaction. So what we did is we looked in the Scopus database and provided the keywords, or let's say the torrefaction as keyword, or included in the title or in the abstract. And what came out of this is that there has been, in the first years, when most ECN started to work on torrefaction, there were some publications, and then from 2007, 2008 onwards, and specifically from 2010 onwards, a lot of publications have been brought into the market on torrefaction. So what this figure shows is year-by-year documents published, so it's not cumulative, but it's year by year. And only last year already about 175 publications has been traced in Scopus on torrefaction. And about 90% of these publications is actually scientific articles. So it means that a lot of information and a lot of knowledge is currently available on torrefaction, both on the process as well as on the product. And so this gives a lot of room for further development of the technology. Now also, let's say the general opinion already in 2014 was that the development of the torrefaction technology was not as fast as was originally anticipated. So what we did is we did this consultation round along the developers and asked them two main questions. The first question what we asked is what have been the main restrictions for development and commercialization of the torrefaction technology? And the second question we asked is what should be done to enable the technology? Now this figure shows the main restrictions for the that we got from the developers on the development of the torrefaction technology. So we asked 11 developers, and 7 out of them mentioned that the lack of policy measures was the main restriction for development of the torrefaction technology. Another 5 mentioned that it was more about standardization, and 4 mentioned that it was by negative perception by the end users. So what does this essentially mean? Now if you look at the policy measures, let's start with the original idea to have a torrefied pellet that is an easy and sustainable replacement of coal in a coal-fired power station. That is also the original thought of the fuel. And then, in this case, for a coal-fired power station, the fuel price, or coal price, determines for a great extent the marginal cost for, let's say, making the electricity. This is important to consider the cost of the coal, which is given here as an estimate. and the cost of renewable fuels, which can be, for example, wood pellets or torrefied pellets, which is given here. So what we see here is, let's say, a typical fuel price in Europe gigajoule, and what we see that there is a difference between the coal and the wood pellets, and this gap needs to be recovered. Now, the main way of doing that normally is by having renewable energy subsidies. So that is the first step. And then if you look closer at the torrefied pellets, we see that the current price of the torrefied pellets exceeds that of the wood pellets. And that has mainly to do with the fact that the torrefied pellets are not as much available at the moment as wood pellets. And the target would be to have about the same pricing for torrefied pellets as it would have been for wood pellets. So therefore, given the market conditions and the chosen, let's say, lock-in solutions for in this case wood pellets, for potential co-firing customers that have already invested in infrastructure, a careful policy approach is needed to support the use of torrefied pellets. Now, a second restriction is on let's say, the trade. And Michael will go more deeply into it. That is the development of standards is important. The first thing what needs to be considered is what kind of product are we trading. So for that, a quality standard is needed. A technical specification of thermally treated wood is currently under development, but the final intent is to have a full technical standard. Then there are specific requirements for production of and handling of the torrefied pellet. That can be in form of an MSDS, which has been developed under the sector project. And then there are certain regulations in parts of the world that are needed for example, for importing torrefied pellets. And Michael will also tell a little bit about that. And finally, we need to ensure that all the biomass we use is sustainable. So sustainability certification is definitely important as well. Then the third restriction that was mentioned is that there is a negative perception by the end user of the product. So I said in the, let's say, the early 2000s, there was a very good introduction of the technology and the product, with mainly done by ECN and some others, with very promising results about the product quality and how it can be used. So that gave a boost to the technology, and in the period of 2008-2012 there were a lot of new initiatives. We saw various demonstration scale facilities with quite significant claims, but at the same time we also faced a financial crisis for which it became more difficult to obtain finance for new projects, and focus has been on torrefaction, and yeah, as Jaap also said, process control was sometimes a little bit difficult. So this made that the perception by the end users on availability and on the product itself lacked a little bit, and that was mainly in the years 2012-2015. That was difficult to gain offtake contracts for the torrefied biomass, and the wood pellet market further developed. So the main chicken and egg problem we faced actually is that there was not enough product available at a quality that was more or less claimed, and at the same time there was also not enough request from the market, so to say, in order to scale this up. So then we also asked what are the main enablers in order to further, and not that we need production scale up. That will help then to win the end user's confidence and also result in a lower product price. A little bit, if you do some simple calculations like we did here as well, then you can look at the demand and on the production side. And if you look at the demand side, for a 600 megawatt coal plant, 10% coal firing with about 6,000 full load operating hours, you would require about 150,000 tons per year of torrefied pellets. If you look what is currently available, most demonstration scale facilities have, let's say, at full-time utilization, have about a capacity of 25 to 40,000 tons per year, and most of them are currently partly utilized. So the global production capacity is about the same size as for one plant 10% coal firing. So the production needs to be scaled up. And if you look at wood pellets, typical facilities somewhere between 50,000 and 200,000 tons. So scale is really needed. Then ways to win the end user's confidence is, for example, to find new markets. And Micha will also go into deeper into this side, and develop the whole chain in advance, which is important for technologies that are still in development phase. Make realistic promises. Ensure the quality of the product. Ensure that the product is also safe to use. And make a tradable product and have the proper standards in place. And then the last question is, in case you would have a product that is, or actually we have a product that has price specification that can be ready to use, but how to bring then the price down. And when you look at our report of 2012, it shows for commercial target price for torrefied pellets compared to wood pellets, and we asked also some utilities about what if, let's say, the torrefied pellets would be available on a large scale, the product quality is as expected, and the fuel price in the harbor is similar to that of wood pellets. Would you consider to use it? And then the general answer was yes, we would definitely consider it. So then the question is it also then possible to have a cost price in the harbor that is comparable to that of wood pellets? And from the calculations, in which also a Torrefaction developer in 2012 was involved, it shows that the torrefied pellets in the harbor could be in the same range as that for wood pellets. So to conclude, we have a process that is well developed with a lot of research and a lot of developers that have gained a lot of experience. We know how the product looks like, but now we have to find specific markets, for example in energy or in steel industry, or maybe a little bit further ahead as part of a bioeconomy, where, for example, you use torrefied biomass and then mill it, gasify it, and use the syngas for further utilization in the bioeconomy. But that could be potential of some markets. Then at the current stage you would need to develop the whole chain, and in order to bring, say, the price down, alternative feedstock types would be a way to go. And one of the example in this context is maybe interesting to see. It is a project that is currently being developed by a number of companies in Indonesia, and it has the reference here also to the YouTube movie, so please have a look. And then finally, with that, I would like to hand over to Michael, and Michael will tell you more about the tradability of the product, going into the details of the supply chain, telling you more about the overall requirements for logistics and trading, as well as new market applications. So, Michael, the floor is yours.
Thank you, Marcel, and thank you for this good presentation about the status of technologies and how some of the actors on the R&D in the sector do see the situation here. Now, I'm going in what is, when looked at the value chain of an energy supply chain, usually called the downstream part. So I'm looking onto the logistics part here, and for this, we need first to see what are the products which are tradable today. It's not technologies which are traded, it's products which are traded. Now, typical torrefaction processes, we see today 3 outputs given in this picture. The chips, which are just the pure output of the drying and torrefaction process, those are going to be densified then either in the shape of pellets or briquettes. For international trade, only the densified biomass is really viable, simply for security and safety reasons, but also for cost reasons. So when we speak about trading torrefied biomass, it's literally always the shape of pellets or briquettes we are talking about. Where are we standing at the moment in this analysis of the downstream sector? I usually present the situation of the overall torrefaction sector with this implication indicator, where we see that already in Marcel's presentation, most of the top part, so the technology and technology development and implementation part is already covered. But we see here in brighter greens also downstream that some of the issues are not completed and have still to be focused on and worked on. This mostly because simply there was not enough volume traded, physically traded today, and there is feedback from the customers and from the consumers needed. So my presentation really focuses now on the downstream part here in this full value chain depiction. When asking for trade, we have to first see what would be the conditions for trade, what is needed for trading. First of all, we saw already in Marcel's presentation that there is the prediction that the logistical costs for torrefied biomass will be significantly less. We usually say between 20 and 40%. Now, how can we prove this? This will be part of my presentation to show that torrefied biomass can be used or can be transported along existing logistical infrastructure. No special requirements will be needed. That was in our report one of the findings from different analyses we undertook. We also have been looking at the standard about the status of standardization. Marcel referred to this briefly. I will introduce you to what the situation is and what we are expecting. And precondition for trade is not only production and possibility of using logistical means, but there is also to be demand, because this is the driver usually for the whole overall value chain. So it is well known and discussed from the very beginning of torrefaction initiatives that torrefied biomass is a good substitute for coal in coal power plants or for co-firing with coal in coal power plants. But is there more? Are there other markets? Are there other sectors in the industry which might be interested in using this fuel? This was also part of what we did analyze in our Task 40 report, and I'll introduce you to the results here. I start with what was one of the preconditions for a very efficient transport, the water resistance. We know that wood pellets, once getting only close to water, are starting to disintegrate, meaning that to build a supply chain for this biomass to the consumers, there need to be a new infrastructure or an infrastructure which prevents 100% that water will come in touch with the wood pellets. This adds cost up to the final product, and torrefied product always claimed, because of the hydrophobicity, that also the densified materials will stay intact when they are in touch with water. a lot of water uptake tests have been undertaken. Unfortunately, there is no standard for water uptake or no definition what it really means, what water uptake is. So most of the producers in the IPTC have been developed their own water test, some research institutions as well. I just present you here the results gained by ANDRITZ, but same also here then shown by results from ECN. Basically, the result was short-term contact with water has absolutely no effect on the torrefied biomass once densified. Long-term contact will on the heap cause that the top layers are getting weaker, meaning that they are losing their durability. They will never disintegrate as well as the as much as the wood pellets on this picture here are doing, but they will become a little bit weaker, so the durability will be reduced. But this only for the top layer in the heap. If you go to the core of a heap, still the old characteristics will be found. Meaning that if on a typical coal yard, torrefied biomass is stored for 1 to 2 or 3 weeks outside, this will have literally almost no effect to the further handling of the torrefied biomass in the feed-in system in the coal power plant or in the industry. If you would like to store torrefied biomass for 2 years outside in rain and frosty conditions, then you have to accept that the durability of the product will suffer from this and the product will be sufficiently weaker. Substantially weaker. Another reason for, or another fear while transporting biomass is biological degradation. Biological degradation has two effects. First of all, you have a mass loss, so you start shipping or start storing a certain quantity, and in the end of your process, you have simply lost some mass and some weight and some value by this, through the biological degradation. And on the other hand, biological degradation also does mean that a lot of carbon monoxide, a poisonous gas, is produced, which, for instance, in the logistical chains of wood chips or wood pellets has caused already quite some bad accidents. Here with this diagram, we found proof that torrefied biomass for sure has a much lower biological activity, and by this biological degradation, than fresh biomass, be it wood chips or be it white wood pellets. We see here that there is sometimes a factor of 2, eventually 3, of lower biological degradation than we would have with white wood. And this stays almost constant, this difference, over time. So unless there is a very, very strong heat source applied to the torrefied pellets, you can estimate that there is almost no or ignorable biological degradation and carbon monoxide resulting from this in the storage capacities. Furthermore, we were looking, transportation always requires, and storage handling requires, that you know precisely, is your product highly explosive or is it not? What dangers are you exposed to? Minimum ignition energy is one of the means to prove how easily a material explodes. Now we all know that pulverized raw biomass, pulverized wood, is very highly explosive. Torrefied biomass does not change this situation, and pulverized torrefied biomass has almost the same or a little bit lower ignition energy values than has the raw biomass. We prove, or with this diagram, we found proof that the explosivity of the dust is not really a result of being torrefied or not being torrefied, but rather a result of what the raw material has been, where pellets or torrefied pellets have been made from. Nevertheless, we know that torrefied biomass is much more brittle than is non-torrefied biomass, meaning that the appearance of very fine dust is more likely in torrefied value chains. By this also sets the requirement for a higher durability and for a very constant durability in the products which are traded, giving eventually even a slight advantage to the briquettes in international trade, simply because the surface and to volume ratio is better with briquettes, and fine dust will always only appear on the surface. Storing biomass, so storing torrefied biomass outside, meaning also exposed to water, that there is some runoff water. Is this runoff water toxic? Is it ecotoxic? We found here from research results in Austria undertaken with Andritz and the research institutes in Austria that there is, once tested according to the DIN standard, the runoff waters and the leaching waters of heaps of torrefied biomass stored outside, that there is no ecotoxicity which is proven or we have to be afraid of. By this, we see that there is, to date, nothing special where we have to see requirements coming for torrefied biomass in respect to any other solid biomass traded. Now, coming to standardization. It was very clear from the beginning that standardization is one of the key elements to make this successful, simply because at the beginning of torrefaction market there were so many confusing expressions, from torrefied pellets to biocoal to black coal to biochar, black pellets, and you name it, how many different names, trade names and so on were developed here. So to make it for the customers clear what the product is they get offered, we were initiating from the very beginning of the IPTC the introduction of a quality standard. And because the ISO 17225 solid biofuel standardization process already started, we embarked on this. Task 40 could report here in its report that the process was well underway, and now, even after the Task 40 report, we can report here that the committee has decided on technical specifications as a first step in the standardization process, a full standard to be expected in 3 to 4 years after some experience in logistics and with final customers is gained. These technical specifications are expected to be released in Q4 2016, maybe Q1 2017. The ISO committee is not the fastest acting organization. That is our experience with it. However, there will be now special classes for graded, thermally treated and densified biomass fuels. They will be separated in different classes according to net calorific value, durability, bulk density, and volatile matter. So there is almost similar to what we see in the wood pellet market, where we see I1, I2, I3, or A1, A2, and B classes. We will have TW1, TW2, and so on. And in parallel to this, there will be a second group of defined products, and this is quite important to me, because here we see that the ISO committee took reference to the initiative of the torrefaction industry, not only to torrefy wood, but also to torrefy agro byproducts or dedicated agricultural feedstock. By this, addressing really one of the core issues of the problems in cost competitiveness of wood or biomass with coal. Wood is simply an expensive product, while several byproducts of the agro-industry and eventually grass plantations would produce much cheaper biomass, by this enabling a much cheaper product at the very end to be supplied to the industry. We see that torrefaction is really a door opener in this direction because of what was addressed already, the reduction of chlorine content, organically bound chlorine content in many of the plants, which can be proven by many technologies, and it reduces, or the problems are then really reduced to alkali and potassium, but this we foresee also as being handled very soon. So torrefaction here broadening the feedstock basis significantly. By this also, torrefaction can become the technology in areas where there is not a lot of forests, but there is a lot of grass plantations or room for grass plantations and other biomasses to be planted. So torrefied biomass is not as sensitive to raw material quality as is today's wood pellet industry. In trading, you need a lot of documentation to make sure or to convince your counterparts, be it a vessel owner or a store owner, that your product is safe and secure to handle. For this, the material safety data sheet was developed together with Sector. This is a standard material safety data sheet, which obviously has now to be adopted by each and every producer and supplier of fuel. In certain regions of the globe, there are certain specific requirements. In Europe, this is REACH. This is a registration database where chemicals which are brought to the market need to be registered. It was for long unclear if torrefied biomass is seen as a chemical or not. Wood pellets is not. Coking coal is not. So we were unclear about is it necessary to register or not. The IPTC for this set up a Substance Information Exchange Forum, a so-called CF, under the REACH and ECHA regulation. This came to the conclusion that there is no registration needed, and whenever there is now somebody producing or trading torrefied biomass and wanting to bring this product to the European market, please get in contact with this CF or with the IPTC to take part in this and make sure that you are also part of this non-need to register the product when bringing it to the market. For shipping itself, it is very interesting or very important that you test negative on IMO 4.1 and 4.2, meaning flammability, self-heating substances. Those proof was given by analysis by VTT and other research institutions. By these, we can prove today, and this is what the report also says, that torrefied biomass is to be categorized as non-hazardous good, which is a very good message, because by this we can prove that all the cost advantages we have expected over the supply chain are really to be realized and can be accounted. For the final consumer, one of the drivers for consumption is how is the greenhouse gas comparison to white wood pellets, for instance, or to other biomasses, and for sure to coal. Now, these results by DBFZ do show impressively that torrefied biomass, almost independent of the raw material source, is much more greenhouse gas efficient than pellets produced from this material without torrefaction in the process. Now, by this, I'm already moving on to the demand side. There is a lot of industries waiting for a biomass commodity which can be applied in existing infrastructure. First of all is the coal power plants and the power industry. Here, quite a number of full-scale burn tests have been undertaken, mostly in Europe. Here are 4 examples shown where you see that the tests were always on a couple of thousand tons, between 25 and sometimes even 100% of co-firing. And all results so far were very satisfying and were very much to move on in this direction. It is just that the whole European power industry had a significant limitations or reduction in growth in co-firing and use of biomass, which influenced not only torrefied biomass but also the standard biomasses burned to date, and and did lead to reductions in consumption by this industry. But there are other industries also out which have started to eye onto torrefied biomass. For instance, the steel industry. For the steel industry, the replacement of coking coal and pulverized coal, which they use sometimes for the activation of limestone and other processes, torrefied biomass is extremely interesting. And the steel industries are usually a significant contributor to the CO2 emissions in the countries where they establish. So this is also a political measure, and they feel some political pressure to undertake certain steps. The chemical and petrochemical industry sees the big potential in torrefied biomass in its ability to produce a very homogeneous and clean gas if gasified. Chemicals can be derived from biomass that way much easier, and all the problems which have been seen and experienced to date with gasification of solid biomasses are to a certain extent overcome with a pre-processing in torrefaction. The pulp and paper industry, by using it lime sludge kilns and as a general coal substitute, is one of the core interested industries, and even more interesting in terms of volumes also is the non-metallic minerals industry for the substitution of conventional fuels in all kinds of kilns. Besides the industrial applications, there are all the heat applications which are today covered with biomasses. Torrefied biomass here qualifies mostly for the larger scale, so district heating, commercial scale heating processes and process energy. First experiences are gained here with district heating already, very satisfying, and one of the key advantages here, for instance, is that due to the higher density of the torrefied biomass, a lower number of trucks need to arrive at the district heating or processing energy plant, and this is for certain very densely populated areas also one of the issues which is a key advantage and seen as something to count. Looking into what are the volumes we might look into by 2025 by sector, you see that we have estimated the non-metallic minerals as by far the biggest, followed by pulp and paper and iron steel industries. Totally, the contribution of torrefied biomass to the overall biomass consumption in biomass could be 1/3 or 10% of the total consumption, which would lead to, pardon me, approximately 300 petajoule of consumption here. 300 petajoule converts in approximately 15 million tons a year consumption of torrefied biomass. If we look into this now by regional distribution, we see that Europe still is going to be the leader in biomass consumption simply because so many measures and political structures have been established already. But the other areas are following. Asia is picking up, particularly Japan and South Korea are picking up here very, very much already. But also North America, Canada, United States, we see growth potential here. And by 2025, there might be substantial volumes of torrefied biomass being substituting, first of all, coal, but substituting also some of the already existing biomass supply chains. Now, to conclude, where are we today? With torrefied biomass in the downstream side, starting with a clear definition of what the product and what the quality is by the ISO technical specification, which will be issued very soon. It is verified that handling and storage advantages along the logistical chains are existing and can be capitalized on, so 20 to 40% cost savings and cost reductions are shown and proven by this. There is already verified the acceptability for co-firing in existing coal power plants. Other industrial applications, other industrial plants like the steel industry, like the cement industry are well advanced in testing torrefied material and will very soon also join the train and will start combusting torrefied biomass in higher volumes. The derivation of energy carriers from non-woody biomass is very, very successful to date and will be implemented on a larger scale also very soon with projects we see in Africa, which we see in South Africa. And by these, we see that we are different to some other technologies. There are several technologies we see in the torrefaction sector. There is much more than only one producer. There is a number of producers. By these, the risk for any large-scale off-taker is also to be split. And by many producers of more or less the same product, this is the precondition for a further commoditization of solid biomasses, and to these the torrefied product will be contributing significantly, especially as the final price of the gigajoule or the megawatt hour at the customer will for sure be competitive to all other biomasses which are consumed by today. By this, I'm concluding, just referring once again to the reports which you can download freely from the bioenergy, IEA-Bioenergy.com site and from the individual task sites. Thank you for this, for listening, and I'm looking forward to your questions.
Okay, thank you very much, Michael. Yes, I think we've spent quite some time on two very interesting presentations, giving a very broad overview of the status of the technology and the possibilities for trade. I would like to ask the moderator, I'm not sure if I can do it myself, yes, to switch back to the chat mode, and I would like to invite all 40 participants, as I can see, to ask their questions through the chat box. So please, if you have a question to either of the speakers, to Marcel or to Michael, please put your questions in the chat box, and then we can address them one by one, because if we ask questions all 40 at the same time, then it will be a bit of a chaos. So whom can I invite to ask a question to either of the speakers? I'm not sure if everybody, yes, Stephen Chuck is giving us a first question. And please do not wait until Stephen is finished. You can type at the same time so we can get multiple questions. All right, so Luke beat Steve, I guess, to the first question. So how do you see torrefaction of non-woody biomass evolving? I guess it's a question for both of you, Marcel and Michael. Who would like to go first?
Marcel, would you like to start?
Yeah, I can start with that one. Yeah, I think that the technology in itself has been focused mainly on woody biomass for the pilot and demonstration scale facilities. But the aim of the technology is to have a fuel flexible technology, and there are also developments for using, let's say, for example, different feedstock. And also a lot of tests have been done with different feedstock types. So it would definitely be a technology that that should be able to cope with different types of non-woody biomass.
Well, and maybe to directly follow up with a second question from Ruben, sorry, also Michael, obviously non-woody biomass has far higher ash contents, which was already mentioned during the discussion, maybe increased even further. They may have high silica content, like rice husk, as mentioned by Ruben. Do you see specific technical and non-technical challenges when using non-woody biomass for torrefaction?
Yeah, basically in torrefaction, the ash content and the minerals content is not influenced. It's just, as said before, the chlorine content will be reduced. However, the amount of ash in reality in biomass is always much lower than is in coal, for instance, maybe with the exception of rice husk. So basically, it's not the amount of ash which is the important or eventually limiting factor, but it's how the ash would behave. So in reality, what is ash melting behavior, and how is the alkali and silica or potassium equilibriums. This is something where now also the consumers are asked to join in and to help the final development. There are measures to handle this, and there is a lot of experience with the coal power industry on how to handle misbehaving ash and misbehaving mineral contents. We do see that this is really a measure or an activity which is worthwhile to spend more time on. Many torrefaction companies have focused on these now, simply because about 40 to 50% of the full costs is the raw materials or the feedstock which is produced, and these to be influenced. So if this cost factor is influenced, the effect on the final product cost, on the final energy cost, will be much more significant than on any other of the links of the value chain. We see here, for instance, that in the palm oil industry, so with empty fruit bunches, with palm fronds, with prunings, there are some activities ongoing. We see, especially in Africa, that there are projects dealing with grasses and with grass plantations, which also have the advantage that some land which cannot be used for other other activities or agriculture anymore is used. So there is a movement into this direction, and now it's really time for the consumers to join in and to help really to find the right recipe, literally, for the product which then can be accepted by them.
Okay. I think that's a clear answer. Maybe you can move on to the next one from Stephen Chuck. And Stephen would like to know how the economics of torrefied biomass stack up against the pyrolysis bio-oil as an energy densification measure. With pyrolysis, we've also seen some recent developments, amongst others in the Netherlands, I think also in Finland. So these are in some way competing technologies. In other ways, they obviously also have different properties, different end markets. But this question is specifically about economics. So I guess the euros or dollars per gigajoule delivered to the end users. Marcel, Michael, how does torrefied biomass compare against pyrolysis oil?
Yeah, maybe I can give a start here. Well, generally for torrefied biomass, we aim to have, let's say, a target price of below 10 euros per gigajoule. As far as I know, for pyrolysis oil it will be higher than that, but the product is also different, and the application should also be different. So, the question is how well would be the comparison to do from an end user perspective.
Yeah, but I do agree with what Marcel said. There is not much to be added. I mean, at the moment, both of the technologies are in a very early stage. It's very difficult to compare the economics yet, because there's simply not enough experience. I'd say that the product of the pyrolysis bio-oil process is simply going into other direction, is covering other markets, and will in its pricing structure later on also be influenced by different market forces than will be the solid biomass sector. So I would at the moment not be, first I would not feel fit for giving here economic comparisons, and secondly I don't think that this is really two things which will be directly in competition.
Mm-hmm. Here. Then from Shabab, and he would like to know, is a torrefied biomass defined by either a specific mass loss or a specific calorific value? Is there let's say a general understanding of in the industry? Is there a specific calorific value that should be aimed for, or is a minimum or maximum mass loss acceptable? Can you comment on this?
That was precisely one of the discussion points in the ISO committee, as far as I understood and as far as I learned from them. The conclusion was, to date, we rather define different steps and different calorific values or mass losses in different categories. So basically, I think the industry agrees that a net calorific value of approximately 21 gigajoule per metric ton is what is the benchmark from where on torrefied or biomass can be named torrefied. This, on the other hand, is almost reachable, or is really based on woody biomass. If you go to agricultural biomass, which is significantly higher ash contents, then already 19 or 19.5 gigajoule might be a significant improvement of the net calorific of the value of the raw material. But please have a look. Once the technical specifications are published, you will see here the different categories and classes which are suggested for the time being, and where the market will start now to pick up on, and we will see if there will be a revision in the next years because of the learning process.
Okay, very good. Then I suggest we skip the question by Terry soon, because the agricultural waste as promising feedstocks has been covered already by the first two questions, and I would like to go on to Pulami Roy. He would like to know the usage of torrefied wood pellets in small-scale combustion systems in the future. How do you see the what are the perspectives there, Marcel and Michael?
Marcel, would you have anything to say
Nobody?
here?
Do you use a small-scale combustion?
There was a question. Marcel just left the room. He
The-
came
the-
back now, so we missed the question.
Yeah, but
Okay, no,
it took a little bit longer, so I had to switch some
let me
rooms,
start
so
if
to say.
Marcel can come in later on. I mean, there were some tests with small-scale combustion systems, even with pellet stoves, for instance, which were all fairly positive. Just said, okay, in existing systems, you cannot use without adjustment torrefied biomass simply because of the higher calorific value. So you would have to adjust the regulation. You would have to adjust the airflow. That is true for smallest scale and small scale biomass or pellet systems. Funnily, or for me personally, it was a surprise that torrefied biomass might pick up as a cooking fuel in Africa, substituting charcoal. There are a lot of initiatives I've seen in South Africa, in Senegal, in Ethiopia, where tests with torrefied biomass from agro byproducts, so from grasses, from straws, to substitute charcoal, which is partly transported for a couple of 100 kilometers to the urban centers, has started, and that looks very, very promising simply because of the exorbitant costs of charcoal in some parts of Africa.
Okay. And maybe to add, earlier this year in January, we had 2 days of workshops, and one was specifically addressing the use of torrefied biomass in small-scale applications. Those presentations from those days are available on, I think, the IBTC website and also the Task 40 website. So if you're interested in more information about this, this might also be a good place to look at. Marcel, you would like to add?
No, I think that is, Michael has already explained it quite well. I think from the technical side, the heat balance in the boiler will shift somehow, and because you have, let's say, higher calorific product that has a higher calorific value than with the wood pellets. But I think that would be the main thing you have to consider. But it's doable.
Yeah. Okay. Then I suggest we move on to Dick van der Kluit's question regarding IMO classification. Is the material classified as non-self-heating for all quality variations, i.e. for torrefied products with high and low volatile contents? Marcel, either of you comfortable?
Yeah. IMO is in process. I mean, if you look to the IMSPC code at the moment, at the materials, you find torrefied biomass in a very unclear description. Sometimes it's almost referred to charcoal, which is very difficult to be handled. So to get this really into a clear classification with IMO and to get this in IMSPC codes clearly defined how to be handled, this is still some work to be done, need to be done. Same with the P&I clubs then based on what IMO is classifying. But the proof and all the testing to make clear to the IMO that it is a non-hazardous good and a non-hazardous product has been done and can be shown to them. This is something which will be done once the technical specifications are out, because based on these technical specifications, then the product for including into the IMSPC is clarified, and based on this we will work.
Okay. Good. Then a question from Taraka Doda Paneli, and I think she is asking what the possibilities of generating more income from side products are. For example, condensing the volatile gases, which are, I guess, mainly used for the internal energy requirements or for power production, and instead producing some valuable products from condensate. Do you see developments there? Has somebody been already experimenting with this to use the syngas or the volatiles and produce, for example, molecules, chemicals, etc.? Michael or Marcel?
Maybe I can give it a try.
Yes.
Well, if you look at the current, it depends. So the amount of torrefaction gas you will get from the torrefaction reactor depends on the residence time and the temperature in the reactor. So if you would typically have a torrefied biomass that's for example somewhere between 21 and 22, 23 megajoule per kilograms, you would get an amount of torrefaction gas that you would normally use for drying the biomass. And I think you can dry it then back from somewhere around 20%, 20-30% moisture content, and that is normally what you would typically have as a minimum moisture content in your biomass when you get it on site. So I think in practice the torrefaction gas will primarily be used for drying the biomass before it goes into the reactor.
But I think, Marcel, you showed this graph on what research on torrefaction, how the number of papers goes up, and I think quite a large amount of these recent papers on torrefaction are focusing precisely on this matter, on how to improve the value and how to derive eventual products from condensating torrefaction gases. However, I'd like to draw your attention also to an initiative, a Dutch initiative, Torgas. They are gasifying torrefied product, and with the gases from the torrefied product, then are trying to derive more valuable products. So they are not taking the same gases from the torrefaction process itself, but the end product of the torrefaction process to gasify these and go into the chemicals derivation with these gases from torrefied product.
Yes.
Okay. I think the next question is also about gasification, and that is, what is the influence of example, tar when torrefied biomass is used in a gasification plant? I assume in comparison to either, for example, coal or woody biomass. Is anybody comfortable to answer that? Maybe Jaap, you can comment on this as well. Does torrefied biomass produce less tar?
Yeah, this is not, I haven't been involved in a specific project on gasification of torrefied biomass, but I would guess that because of the lower moisture content and the higher energy, or the higher heating value of the fuel, you would have a higher gasification temperature, so that would be an advantage for the process. So you could have in principle have a lower amount of tar in the gas after torrefying it. So more similar to coal, I would say. But maybe there are more people in the audience also that know better about this.
What we learned from
we can open up
from a European utility. They had used torrefied biomass in one of the large-scale gasifiers, substituting coal there, and they were very satisfied with the results. The only issue with them was that the ash content was too low, and they needed a higher ash content to build a certain fluid in the gasifier, which usually was the ash content of the coal. That was the only limitations I have heard of. Torgas itself, if we speak about the torrefaction or the gasification process from torrefied product, and this is something where I really would need to address them, because all their findings are at the moment under disclosure. So it's nothing which they published to date.
Okay, I think we have plenty of more questions, so we need to watch a little bit time, but I think we have 4 or 5 left. One is again about a technical question. Jaap, you showed the behavior of torrefied biomass in a large-scale boiler compared to coal. Now there's another question, how torrefied pellets behave in a medium-scale heating plant of, for example, 5 megawatts, I assume thermal in. Can you comment on that?
Yeah, well, it depends how you compare it with, say, if you compare it with a biomass plant, well, you will have a very similar combustion as biomass. It's just that, as Michael already explained, you have a higher heating value, so you need to adjust the airflow a little bit, but this is all doable. This was also demonstrated in the sector project, I think, that combusting torrefied pellets on a grate fired boiler is possible. You just need to change the air settings. So not in a standard pellet boiler that is already in use. If you use torrefied pellets there, then you might have some agglomeration, for example, because combustion temperatures may be higher, and also the volumetric energy density is higher. So that needs to be changed. But in principle, technically, it's all no problem.
Okay. Then I think we have a question which was slightly touched upon already by Michael before, by Hamrasin Achari, and he says that the prediction is that by 2025, Africa and Brazil will be the global leaders in biomass use at 35 and 43% respectively. I'm not sure where those numbers are coming from specifically, and I assume that they also include the traditional fuel use, especially in Africa. And Hamrasin is wondering that in Africa, specifically torrefaction does not seem to be a chosen technology. What are the economic and technical factors for this prediction? So, Michael, as you mentioned Africa and torrefied biomass replacing charcoal already, would you be comfortable on commenting on this?
Yes, obviously. The referred percentages are for all biomass to be used. So these high percentages you're referring here, and which are in the table, they are under the column biomass as such, and not torrefied biomass. And this is referring to the already existing very large proportion of biomass in the energy balance. In Africa specifically, Africa is not different to the other continents. I mean, you don't have a high density of torrefaction plants anywhere in the world. Maybe outside the Netherlands, where there is a lot of demonstration plants, but otherwise they are very thinly distributed. So Africa is not different to other regions. I personally have been looking into some projects in development in Africa. They are mostly focusing on non-woody biomass, and basically from the economics and from the technical viability, they look very, very good. Political stability or the viability of the project from an overall economic point of view, I cannot judge. I think that torrefied biomass does have a very, very good future in Africa, because there are some of the economies really booming with a shortage of electricity, with a situation where a lot of the electricity is consumed for cooling, where torrefied biomass can fuel decentralized small-scale power plants, which can be then connected with absorption chillers and fuel district cooling systems as well. So torrefied biomass can be here a solver for a solution to problems existing, and especially existing nowadays in Japan and eventually Southeast Asia.
Very good. Marcel, would you like to add?
No, not specifically. Yes, I don't know. Let's say I would not know the reason why torrefaction would not be a chosen technology for Africa. I think there's different industries, and where the transportation distances are large, like also in Africa. Then there's definitely markets available for the torrefaction technology. But for now, like Michael also said, for now, its current development state, still work needs to be done.
Good. I think the next question is about, for both of you, and that is about steam exploded wood pellets, which is obviously a different technology, which yields typically, for example, somewhat lower heating content, but they are in a way an intermediate between wood pellets and torrefied wood. Were steam exploded pellets included in either of the studies, and how do you see their future compared to those two options?
Yeah, that's an interesting question, because with a number of tasks, including task 40 and task 32. We are currently working within the IEA Bioenergy on a comparison of different pre-treatment options and steam explosion technology, as well as torrefaction technology and pyrolysis. They are all included in this comparison.
Yes, and I'd like to.
And Michael, for the task 40 study?
Yeah, steam exploded pellets were not included in the task 40 report as such. However, I'd like to remark, or two further remarks. The IPTC is currently undertaking a study, a comparison between different technologies, their mass and energy balances. And second, and this will be available most likely December this year. Second remark, the technical specification from ISO does show clearly that at the very end, it is not the process and the pre-treatment technology which is the important thing, but it is the product which is traded, which is standardized, and the product which is then arriving at the customer, independent of what pre-treatment processes they have been done. This is also one of the reasons why there are different categories and classes in the standard, starting or having one class with a very low calorific value of, I think, 18 or something like this, so that there is room also for steam exploded pellets to enter into this standard of biomasses by thermal treatment.
Okay. Good. The next question again is I think a fairly technical one. Takahiro Yoshida has apparently also been working on pelletization of torrefied material and actually found that the energy required to pelletize torrefied material is higher than of woody biomass. Do any additives have to be added in order to minimize pelletization energy, he is wondering?
Maybe I can briefly answer that one. As far as I know, and also what we found in the sector project is that most companies involved in pelletizing torrefied biomass add water to make it easier to pelletize the product in the end. So a little bit of water helps a lot. Is the experience, I think, in general agreement. So no additives, but some water.
Yeah. And I know from practical experience also that in some cases also steam is used for the densification process.
Yeah. Good. And then we have a more general question again from Joosten Hornton. He's wondering whether torrefied wood or torrefied biomass in general is a optional input for a biochemical, I guess, biorefinery, as the torrefied wood is basically deconstructed and doesn't contain any sugars anymore. And if so, would that not endanger the long-term future of torrefied wood compared with white or steam exploded wood pellets? If no one of you is really or comfortable for answering this, then I can also give it a shot myself. I think it really depends on what kind of biorefinery you're looking at. I think we have biochemical refineries, and indeed their sugars are often a platform chemical which you want to use. And torrefied biomass obviously does not contain any sugars anymore, but obviously, as we discussed earlier during this discussion, you can also gasify torrefied biomass, where torrefied biomass has definitely advantages over normal biomass. And from the syngas, you could also produce a variety of chemicals, fuels, also power. And so in that sense, I think torrefied biomass could be a good feedstock for thermochemical biorefineries, but obviously not or barely suited for biochemical biorefineries. Michael, Marcel, Jaap, anything to add to this?
Not really.
I think that's not very well said. I fully agree with that. Yeah.
Good. I think we have run through all of the questions. We have also run a little bit over time, but I think it was worthwhile, definitely worthwhile. Many good questions, good answers, a very good overview of the field. I would like to thank all of the presenters very much, and also, of course, everybody who participated in the call, in the webinar, asking questions. I think it was a very valuable exercise, and I would like to point out that the entire webinar will also be published on the IEA Bioenergy website and on the CIF websites. The presentations will become available online, so if you would like to forward this to any of your colleagues, please do. If you would like to look back at the presentations, there will be plenty of opportunity. Unless there are any final questions or remarks from the speakers, I think not. Then I would like to close this webinar. Thank you again for participating, and keep a lookout for further webinars from IEA Bioenergy in the future. We typically publish 1 or 2 every 3 months on topics like cascading or on greenhouse gas balances, etc. So if you're interested in more information about bioenergy in general, please keep a track on this. So thank you very much, and have a great day.
Thank you as well.
Thank you very much, everyone.
Thank you.
Thank you.